So our thinking is that integration is multiplication, but one of the factors is variable. And we have to think, what does that mean we have to do? What does that mean integration is? How do we multiply when one of the factors is variable? One of the nice things about this is that we all already know how this works. Let's think about multiplication, but one of the factors is variable. Multiplication. Let's think about what multiplication is, and then think about what it'll mean for multiplication with one of the factors being variable. So, if I write the expression 3 times 5, we could think of this as a 3 plus a 3 plus a 3 plus a 3 plus a 3, or 5 plus a 5 plus a 5. Multiplication is repeated addition. That's why we have multiplication, because we realize that if we just had addition, it's like, oh, this is a pain to just add this up all the time. Let's speed that up and do multiplication. Multiplication is repeated addition. Multiplication is repeated addition. Multiplication is repeated addition. 3 times 5 means either we have 5 3s or 3 5s. Here's multiplication. And here's repeated addition. Multiplication is repeated addition. When all of the terms in our sum are the same, we get to multiply. And that should sound familiar. When all the terms are the same, we get to multiply. When all the terms are the same, we get to multiply. I see this long addition, 3 plus 3 plus 3 plus 3 plus 3. It's 5 3s. So I'm going to skip that addition. I'm going to summarize it with multiplication. I'm adding a bunch of stuff, and all that stuff is the same. It's all 3s. It's 5 3s. I see 3 5s, 3 times 5. We get to do multiplication because all the terms are the same. When all the terms are the same, we get to multiply. I should say addends. I keep saying factors in multiplication, but I always say terms for addition and subtraction. Oh well. I guess it's because I don't want to make a difference between minuend and subtrahend when they're all just addends that are opposites anyway. All right. If the terms are not the same, then we're stuck with addition. If the terms are not the same, then we just do addition. So with 3 plus 3 plus 3 plus 3 plus 3, I can say that's just 5 3s, and I can use multiplication because they're all the same. But if the terms are not the same, then it's just an addition problem. I don't get to summarize with multiplication. So if I have 1 plus 2 plus 3, terms are not the same, we just have to add them up. We don't get to multiply. We just add, we don't get to multiply because the terms are not the same. It's not repeated addition. So the terms are not all the same. So we don't get to multiply. This is the same situation we found ourselves when we were calculating area. If the length is constant, then we get to multiply to find the area. But if the length is variable, we have to do something else. That something else is going to be integrate. We integrate the length over the width. If all the terms are the same, that is, if the terms are constant, then we get to multiply, and life is easy, and we're happy. But when the terms are not the same, we can't multiply. I can't do 1 plus 2 plus 3 and say, well, that's multiplication, unless I start changing what the terms are. It's not about looking at what the sum is, it's about looking at what the terms are. So that's phase 2 of integration. Part 1, integration is multiplication, but one of the factors is variable. Part 2, integration is addition. That's part 2. Part 1. Integration is multiplication, but one of the factors is variable. When we look at multiplication, we see that multiplication is just repeated addition. So, phase 2 of integration. Integration is addition. Phase 3 of integration incorporates the calculus part, where instead of adding over a discrete sum, where we have discrete terms, we're adding up over a continuum. That's phase 3, the calculus part. I need the page. Page 3, phase 3. The calculus part. Our addition is not going to be with a discrete number of terms, but over a continuum. Rather than adding up discrete terms, we're adding up over a continuum. We're adding continuously. So it's a continuum rather than a discrete sum. Let me write that well. So rather than having a discrete sequence of terms, we have a continuum of terms. Rather than being able to point to the first term, the second term, the third term, rather than looking at things in terms of integers, we're going to look at things in terms of of real numbers, where it just flows from one to the next. We can't put a plus in there because they're infinitely many. That's how calculus comes into it. Our addition will have an infinite number of terms. Any questions? The way that we're going to make this work is we're going to model the continuous addition with discrete addition. We're going to model a continuous sum with a discrete sum. Any questions? let's just quickly summarize what the technique is going to look like. So let's suppose that's supposed to be a y. Let's suppose that we have a really curvy, wacky function. Now, so I've just drawn a line, and I'm going to say the area under this curve from x equals a to x equals b. And everybody's going to be, that's just a trapezoid. Why don't we just do trapezoid stuff? It's like, well, it's not always going to be a trapezoid. The point is not finding the area. The point is understanding how the area can be found in a calculus way. So what I want to do is evaluate this function at all these points between a and b. But when I say all these points between a and b, I can't just evaluate the function and add those things up. There's an uncountable infinity of values between a and b, an uncountable infinity of real numbers between a and b. I can't just plug in a and then plug in the next thing, because there is no next thing. Whatever real number you're starting with, there is no next real number. So what we're going to do is we're going to model the continuous sum with a discrete sum. I can't evaluate the function at a and then evaluate f at the next real number, because there is no next real number. There is no next real number. That's the nature of continuity. There is no next real number. So what we're going to do is we're going to break the interval up into pieces. And we want to use multiplication. We're going to assume that the function is constant on each of those pieces, because there's no next real number. So we have to build our own next real numbers. There is no next real number, so we build our own. So I'm going to say divide this interval into two subintervals. So it's going to be x0, and now I'm going to say this is x1, and this can be x2. And what we're going to do, after we divide the interval from a to b into just two subintervals to start with, I'm going to assume that the function is constant over each subinterval so that I can get away with multiplying. We will assume that the function is constant we assume that the function is constant on each subinterval. That way we get to use multiplication on each subinterval. So what I mean is that between x0 and x1, I'm just going to flatten out this function. And I'm going to say this is an approximation of the area under that curve. Flatten it out. Then I'm going to do the same thing in the second subinterval. And so we get another approximation, and it's just rectangles. So we get to use multiplication, length times width. So I'm going to say this is, say, delta x. That's some small change in x. And then this first rectangle is going to be the function evaluated at x0 times delta x. And then I get to add because I want to multiply, but I can't because everything's different. And then I'll just evaluate the function at x1 and multiply by delta x. And that is an approximation of the area under the function f of x and above the interval from a to b. Now there's some stuff that's missing. But we missed some stuff. Colson. Yeah, there you go, buddy. Job. Did you hear somebody out there? Good job. Can you sit? Touch. Thank you. Good job, buddy. Good job. Can you lay down? Good boy. So shy. Okay, chill. It's like 1 more minute. I know you don't know what a minute is. My dog doesn't know what a minute is. So yeah, I know. Colson, come here. 1 minute. Chin. Yeah, good boy. So we missed some stuff when we made this calculation. We missed all these two little triangles up here. But we only broke the interval from a to b into 2 subintervals. So we're just going to use more. And if the answer is to use more subintervals, and we are in calculus, we're going to use infinite subintervals. Any questions? So these are the 3 phases of thinking about integration. Phase 1. Integration is multiplication, but one of the factors is variable. Since integration is multiplication, and multiplication is just repeated addition, where all the terms are the same, integration is also addition. If everything's the same, then we get to use multiplication. But if things are not the same, then we have to use addition. We drop it back 1 to addition. That's phase 2. Phase 3 of integration thinking is the calculus parts. We're going to add continuously. Rather than making a discrete sum, where we have terms 1, 2, 3, or even terms 3, 3, 3, 3, 3, now we have an infinite number of terms between a and b. Problem is, there is no next real number. Pick a real number, there is no next real number. So we build our own. We take what our continuous sum is, what we want for our continuous sum, and we drop it back into a discrete sum. And then we change our model to have more terms. And then we're going to start thinking of our continuous sum as the limit, as the number of terms goes to infinity. So we missed some stuff, and the summary is we use more terms to miss less stuff. So let's pause the video here because that's the end of class. Let's pause the video here, and then tomorrow we'll draw more pictures of this, where we take our continuous sum and model it with a discrete sum.